Okay, hi everyone. We're going to walk through what a mole actually is, just to give you a little bit better of an idea of what this quantity is that we're going to be talking about over the next couple of days. So a lot of this can be attributed to some work that was done by Amedeo Avogadro. We already talked about him when we talked about Avogadro's hypothesis. He was an Italian lawyer, but in his spare time, just because for fun, he'd like to do some physics and chemistry on the side. He was making observations with the gases, and we know that he used those observations to come up with his hypothesis that if you have different containers that were the exact same size under the same temperature and pressure, that you'd end up with two particles, or total number of particles that would be the same in those two separate gases. Avogadro's number, which is one thing that we're going to get very familiar with here in the next couple of weeks, was something that was established by other scientists. They named it in honor of him because based on the work that he did. He actually died in 1856. So when we talk about what a mole actually is, what we're really looking at is just a regular quantity. It's a number. It's a number that we're going to use to count particles. And just like we can use words to represent other numbers, we see that all the time when we talk about things like a dozen eggs, a ream of paper, a barrel of pennies. These are things that we can use to discuss a quantity that simply just means something else. So for example, if we talk about a dozen, we know that means 12. A ream of paper, if you didn't know, it's a stack of sheets of paper that you get from printer paper, usually 500 sheets of regular thickness paper. A barrel of pennies, we can quantify this any way we want, but let's say that we determine that a certain barrel of pennies had 24,216 pennies, we could say that's one barrel. So if I told you you had 3 barrels, you could easily figure out how many pennies that is. If I said you had half a barrel, you could figure out how many pennies that is. So we can use these names just to simply represent a number. In this case, we know that what we're going to be using this for is to talk about these particles, these things that we've been calling particles or atoms. It's not practical. In fact, it's not even possible to count each one in any given substance or any type of matter. The size of these things is just way too small. So for example, if we had a barrel of pennies and we wanted to start talking about counting them by weighing them like we did earlier today, would we be able to count, would we be able to actually utilize a barrel that contained different things in it, like nickels, dimes, and quarters? And the answer you should figure out is no, that it can't. You can't do that at all. We'd have to make sure that we have some sort of reference that's all the same. It has to be a pure substance, something where the particles or the smallest component of that are all exactly the same thing. So in this case, we're going to be talking about atoms. It's got to be one atom of one element, or a molecule of a compound. So just like a dozen is going to tell us something, we know that we've got 12 of something if we have a dozen. A mole is going to tell us the same thing. But instead of 12, a mole is a gigantic number that is going to be really difficult for you to even picture how big it actually is. And that number is 6.02 times 10 to the 23rd. So just like a dozen equals 12 of something, a mole equals 6.02 times 10 to the 23rd of something. Avogadro's number is that number. And by definition, it is of any elementary entity. So if we're talking about elements, we're talking about the most elementary entity is an atom. If we're talking about compounds, the most elementary entity is a molecule or a formula unit, which we'll define in more detail later on. If we're talking about a mole of gorillas or a mole of anything else, for gorillas as an example, it would be one gorilla. It would be an elementary entity of a group of gorillas. So a mole of atoms, a mole of molecules, a mole of gorillas, they would all equal the exact same value, 6.02 times 10 to the 23rd. So how big is that number? So if you started counting, is it even possible to get to a mole? Well, if you started counting and you went 1 second for every single number that you counted, which is pretty slow, but for the most part, this will be easy for us to see the math here. If you did that, it would take you 1.9 times 10 to the 16th years to count to a mole. Now, just to put that in perspective, how big is that? 1.9 times 10 to the 16th years. Well, the Earth is only 4.53 times 10 to the 9th years old. So if you look at the difference between those two, it's actually 4 billion times longer. It would take you 4 billion times longer to count to a mole than the Earth has actually been in existence. What about another way of looking at that? Well, if we want to take paper and we want to stack paper up until we got to the moon, you would need 159 billion stacks of paper, with each of those stacks being from the Earth to the moon, that tall, in order for you to get a mole of sheets of paper. It's a gigantic number. It's a huge, huge number. One of the things we're going to be able to use this for is to talk about things like molar mass, which is a new concept that we're introducing today. Molar mass, by definition, is simply the mass in grams of 1 mole of any substance. If it's for an element, it's really simple. We can look at the periodic table, neon for example, we can find out what the atomic mass is, and we're going to utilize that atomic mass and determine that for the units here, we're using grams for every mole, that neon would have a molar mass of around 20 grams for every mole. For a compound, the mass is going to be of each of the individual elements but added up. So let me show you how to do that really quick. Water is an example of a compound that we're familiar with. So you've got two hydrogens, one oxygen. For each hydrogen, if you look at the periodic table, it's got a molar mass of 1. There's 2 of them, so we have a total molar mass of 2 for the hydrogens. For oxygen, there's only 1 of them, and it's got a total mass of 16. So for each one of those, again, we have 16. If you add those together, you end up with a total of 18 grams for every mole. That means that if you have 1 mole of water particles, you have exactly 18 grams of water particles. The molar mass is the value, the conversion factor that we're going to be able to use to go back and forth to convert between things like moles and grams. It's going to make it really easy for us to do that. Let's do a couple examples. So why don't you take a second right now and see if you can figure out how to do this one. So find the number of moles and 47 grams of oxygen. Don't forget that oxygen is one of our diatomics. So work on this and we'll check it in just 1 second. Okay, so hopefully you were able to set this up and solve for this and figure out how many moles you'd actually have in 47 grams. So when we look at doing these conversions, they're usually one-step conversions, and using the conversion factors like we've used before this year, you usually start with what we have given to us, which in this case is 47 grams of oxygen. Don't forget that oxygen is a diatomic. That's really important here, because when we look at the molar mass of oxygen, it's not just O, it's O2. So for every 1 mole of O2, we have 32 grams of oxygen, because each oxygen atom is going to have a mass of 16. Since we have 2 of them, we're going to have 32 total grams. So if you solve this, we're going to cancel out grams. We end up looking at the only unit we have left, which is moles, which is what we want. And then if you go ahead and carry through by multiplying on top, dividing by what's in the bottom, you're going to get 47 times 1, divide that by 32, and you get 1.46. Your units in this case is going to be in moles. And so if you have 47 grams of oxygen, you've got 1.46 moles of oxygen particles. But how many molecules would that be? Well, if you have 1.46 moles of oxygen, how many O2 individual particles or molecules is that? Well, in 1 mole of anything, we've got 6.02 times 10 to the 23rd. So we're going to be able to use that as our conversion factor here. So we're going to start again with 1.46. This is the number of moles that we had. This is the conversion factor in this area right here that we need to figure out what we're going to use. 1.46 moles, how many actual oxygen particles is that? Well, if it was 1 mole, it's 6.02 times 10 to the 23rd. Since it's 1.46, we know it's going to be slightly bigger, around 50% bigger. So we know the number itself is going to get bigger, so 1 mole is going to go on the bottom. 6.02 times 10 to the 23rd is going to go on top. This allows us to cancel out moles of oxygen on the bottom and the top here. If you multiply 1.46 times 6.02 times 10 to the 23rd, you're going to end up with a value of 8.79 times 10 to the 23rd. So this is then the total number of oxygen molecules that we have in exactly 1.46 moles of oxygen. So how big is an actual mole of particles then? If we want to look at things that we're going to be using on the periodic table, how large would that be? So what I want you to do right now is just picture in your head for a second, if you have a sample of metal, for example, if you have copper, something that you guys are all familiar with, if we have copper, how large would a sample of copper be if it's exactly 1 mole? What physical space would that take up? Well, at first you're probably inclined to think about the fact that that number is so big, so it must be a huge space, but keep in mind that these particles are really, really small. And so I've got 4 samples of different metals here that I'm going to show you just to give you an example of how big exactly 1 mole is. So using the ruler, we can see kind of size-wise scale how big they are. So zinc, aluminum, copper, and steel. I threw a pen down there just so you can get an idea of scale of that. These are pretty small pieces of metal, but each of these contain exactly 1 mole of particles of zinc, aluminum, copper, or steel. So because these particles are so small, we can have such a gigantic number and still make sure that they're all contained in a relatively small area. All right, hopefully you have a little bit better understanding what a mole actually is. We're going to keep working with this, and this is going to be a concept that we use for the rest of the year. So if this doesn't really make a whole lot of sense, please make sure you come check in with me.